When we estimate parameters by least squares regression, we'd really like to know what's the uncertainty of our estimates. Well, assume that the true parameters are given by beta sub a. The estimated parameters we'll call beta hat sub a, and we know that they're equal to the inner product of the dual trial vectors with the data vector. Now, if the data actually do follow the model, then they are parameters times trial vectors plus noise. In that case, the estimated parameter value is the inner product of the dual trial vector with the sum of parameters times data values plus noise. Now, we already showed that the inner product of a dual trial vector with a trial vector gives the Kronecker delta. It gives 1 if they're the same trial function. It gives 0 otherwise. So the estimated parameters are equal to the identity matrix times the true parameter vector plus the inner product of the dual trial vectors with the noise. That's just identity matrix times something gives something. So the estimated parameter is equal to true parameter plus inner product of dual trial vector with noise. When the noise is zero mean, so its expected value is 0, that's one of the assumptions of least squares regression, by the way. That means that the expected value of this inner product is 0, so the expected value of the parameter estimate is equal to the true value of the parameter estimate. That's the definition of an estimate being unbiased. So we have the result that least squares parameter estimates are unbiased estimates. And that's a good thing. Now, the deviation of a parameter estimate is just the difference between the estimate and the true value. And that is equal, as we've just shown, to the inner product of the dual trial vector with the noise values. By the way, something I perhaps should have made more clear at the very outset. In this equation, the index A is repeated, but it's not repeated in a product, it's repeated in a difference. Well, the Einstein summation convention only applies to indexes that are repeated in a product. So it doesn't apply in this case. There's no summation over A values. It's just the difference between A values. Well, the product of the deviations for two different parameters, possibly different, possibly the same one, is just deviation of parameter A times deviation of parameter estimate B is deviation of parameter estimate A times deviation of parameter estimate B. Now, in writing this equation, it occurred to me after looking at it that I just used one of the most extreme examples of possibly confusing notation that's possible. I have used the Greek letter beta as a variable. I've been using it all along to indicate the parameter values, but I also used it as a subscript, an index value, here on psi dagger sub beta b and epsilon sub b. Those two uses of the Greek letter beta have no relationship to each other, even though they're the same Greek letter. It really is an abuse of notation. I did it because when I write index values in Greek letters, I tend to start with alpha and then beta, gamma. I just go through the Greek alphabet, and I did it without thinking. And I finally noticed that here I'd used the same Greek letter in two different ways to mean two completely different and unrelated things. I've used it as a parameter, as a kernel symbol all along to be the parameter values. And here I'm using it as an index, which happens to be summed over because it's repeated in a product for the Einstein summation convention. Those two uses of beta are totally unrelated. Using the same Greek letter for both is definitely confusing. Why would I do this confusing thing? It's habit. Why not just use a different Greek letter for the subscript so it won't be confused with the beta being used as a variable? The truth is, it should be. It would be better formed to do exactly that. But sometimes I actually do use the same letter to mean one thing as a kernel symbol, beta being the parameter value, and another thing entirely as a subscript. Beta is some abstract index. Is this confusing? Yes. Is this bad form? Yes. Do I sometimes do it? Unfortunately, yes. I hope you can overlook my quirkiness. Let's get back to our derivation. If the noise is white noise, which is one of the assumptions behind least squares regression, then the expected value of the product of two noise values is variance times the Kronecker delta. The Kronecker delta is equal to 1 when the two indexes are the same. It's equal to 0 when they're not. This gives us that the expected value of the product of two parameter deviations is the product of dual trial vectors times the variance times the Kronecker delta. Now, because of the Einstein summation convention, this represents a sum over all alpha values and over all beta values. But the Kronecker delta is non-zero only when alpha and beta have the same value. So those are the only terms that really survive in the sum, and what I'm left with is variance times the sum over all alpha values of dual trial vector A and dual trial vector B. Well, we saw earlier that the inner product of two dual trial vectors gives the inverse S matrix. So we finally conclude that the expected value of the product of two deviations of parameter estimates from their true values is equal to the variance times the inverse S matrix. This is the variance-covariance matrix of the parameter estimates themselves.